This lesson I want to talk a little bit about number systems, particularly the binary number system. It's very important to the study of computers in general, and there's a couple of reasons why that is. But first, let's define some of the terms that are involved. What does decimal numbers mean? Decimal numbers is the system of numbers that we already use. We often call this base 10. This is the base 10 number system, the way you're already familiar. The numbers 0 through 9 represent the decimal values. Why is it called base 10? Well, base 10 means that there are 10 distinct symbols that we use to represent numbers in our number system. Though we can make numbers that are much higher than 10, and we often do, we only have 10 distinct ones. Those are the numbers 0 through 9. If you will think about it, every number that follows the number 9 is a combination of one of the first 10. So that's why this is called base 10. Why would we use another number system for computers? Why do machines need the binary system, and why do we have to do these conversions? Why do we have to know something about this? Well, first let's define what binary means. If the decimal number system that we use is called base 10, then the binary system is called base 2. So what that means is the same thing that base 10 means for decimal. It means there are two distinct symbols. So really there's only two possible numbers. There are only two types that are allowed in the binary system. Why would base 2 fit well? Well, it's a very logical reason why. The way in which memory is stored in computers or machines is simply a switch, and the switch can either be on or off. Since there are only two states that there could be, there aren't 10 states, there are two. It's either on or it's off, and we like to represent that as a 0 and a 1. So if you never understood before why we have to deal with binary numbers, that's why. Machines can only think in terms of two states, and we have to find a way to represent it. So this presents a problem for us. It means that we have to find some way to transfer numbers that we recognize into numbers that a machine would recognize, and vice versa. So what we're going to do in this lesson is talk about how to convert numbers from decimal to binary. So let's take a reasonably large number in decimal form. That number is called 248. If we don't call it 248, we seem to know intuitively that it is 248. We learned to count usually by the time we start kindergarten. So we've kind of forgotten why we increment numbers the way we do. Our minds do this rather automatically. Our minds do not do this automatically when we want to count something in terms of binary. So let's talk about the binary digits themselves and how to make them something that represent meaningful data to us. 2, 3, 4, 5, 6, 7, 8. So here are 8 spaces in a computer's memory where I want to store some data. As I said before, data is stored in switches. These are in switches that can either be flipped on or off. So this is going to be some string of zeros representing off, or ones representing a switch that's turned on. So here's one. Here is a string of 8 digits. So for these 8 digits, we're going to put 248 away for now. These digits, I want to know what that represents if I wanted to think of it in terms of a decimal number that my mind can understand. So what is this exactly? Well, first, it's useful for us to define what this means. A group of 8 of these switches, and by the way, these switches are called bits. 8 of them put together, we like to call a byte. Right, so this is a byte of memory, 1 byte. These days we're talking in terms of megabytes and gigabytes and even terabytes and much larger units of memory. At the very basic unit, we're talking about just 8 spots in memory. Those 8 spots in memory are called a byte. We like to look at them from as though you might be reading Arabic or Hebrew, from right to left. So in the rightmost place, if you think of this number as 2 to the 0 power. Why 2? Because this is base 2. We're talking about base 2. If we were doing this in base 7, then it would be 7 raised to the power of some number. But here we're in the base 2 system. So this first place is 2 to the 0 power. If you remember your math, anything raised to the 0 power is 1. So we could call this the ones place, right? This is just like counting decimal numbers. When you taught a child or someone in elementary school to know that this is the ones place, and this is the tens place, and this is the hundreds, but instead of base 10, we're going to do this as base 2. So what would come next? Would you guess? It's 2 to the first power, right? And 2 to the first power is 2. So you could think of this as the twos place. And as I move from right to left, the exponent increases, right? 2 to the second power. 2 to the second power is the fours place, right? That's an S, if you can't tell. 2 to the third power, excuse me, is the eighths place. 2 to the fourth power is the 16ths place. 2 to the fifth power is the 32s, 32, and so on, right? Okay, so how would I transfer this from binary to decimal? It's really pretty simple. If I have the bit flipped on, another way of saying that the switch for that space in memory is turned on, or in other words, that there is a 1 at that location, then I can write down the number. If I don't, there's nothing stored there. So if you notice in the ones place, I have a 0. So there is no 1 in this number. In the twos place, I do have a 1. So I can record that there is at least 2 in decimal form. In the fours place, I also have 1. So I'll add 4 to that list. There's nothing in the eighths place, so I move on. In the 16ths place, there's also 1. In the 32s place, there is also 1 there. And I have 0 and 0 out after that. If I add this column of numbers up, 32 plus 16 is 48, plus 4 is 52. So this number is actually 54 in decimal format. So this string of binary bits, binary digits as we might call them, represents the number 54 in the decimal scheme.